Thanks everyone for joining and welcome to this talk about unified batch and stream processing in Python. A quick summary of what we're gonna talk about, or really the only thing you should remember when you leave this talk is that with the right tooling, you can reuse your batch code in your stream jobs. So a quick outline of what we're gonna talk about. We're gonna start with an example where we're gonna write a batch job, and in this batch job, we'll calculate features for a machine learning model, probably something you guys do every day. And then we'll move on to re-implementing this job so it can serve the features in real time. So we'll go from a batch job to a stream job. And while doing that, we'll realize that it's a lot of work and it'll be much easier if we could reuse the batch code instead of having to re-implement it. And we'll see that to do that, we'll need two things. We'll need a better representation of the data using Apache Arrow and a framework to orchestrate the execution with beavers. So a little bit about me. My name is Arthur Andres. I'm a software engineer at Treadwell Technologies. You can find me on GitHub as 0x26res. So as promised, we'll start with an example. So at Treadwell, we help our client buy and sell corporate bonds. Corporate bonds are a financial product that trade very sporadically, and it's very hard to know their prices. And part of our client offering is a state-of-the-art and industry-leading corporate bond pricing model. So it's basically a machine learning model, and it has some very complicated features. All features come from various data sources, and those data sources have got a heterogeneous data structure, as well as they come at very different frequency. And we do a lot of complicated temporal joins between those different time series. It requires a lot of historical data, but in the meantime, it also requires us to have the latest data in order to make accurate prediction. So we actually, when developing our pricing model, we spend more time on the features preparation than on the calibration or the inference. So let's look at a specific bond and understand exactly what the problem is. So here we've got this bond 007. Maybe you've heard of it. It's quite a popular bond, actually. And there's a lot of observations. Therefore, it's easy to predict its next price. We move on to the next bond, 008. Probably never heard of it. It's not as popular. There's fewer observations, and it's very hard to predict its next price. So we spend a lot of time looking at the data, squinting very hard at it, and we figured that those bonds are correlated. They move together. So what we would like to do is use information from bond 007 to predict the price of 008. So we start with observation, so a timestamp, a bond, and a price. An observation is basically a trade that happened in the market, and from this trade, we can get the price. We get a prediction request, which is just a timestamp and a bond, and it means that we would like to predict the price of this bond at this given timestamp. And in this example, the features we want to calculate are the previous price for bond 008. So what was the price of bond 008 the previous time it trades? And also, a second feature is how much did 007 change since the last time bond 008 is traded? So these are our two features. So visually, it looks like that. We go back in time to find the previous trade for bond 008, and we look at how much 007 has changed. We start by doing a batch implementation of this job. So in this example, it looks like this. We've got observations in a CSV file, prediction request in a CSV file. We load them. We feed them to a Python function. We get the features. We save them in a CSV file. And really, the key point to remember here is that we want to calculate some features. We have a Python function that takes some data frames in and spit out some data frames. It does some complicated stuff. It doesn't really matter what it does. In order to do that, it requires some history of its inputs, in particular the observation. We need an history of it in order to calculate relevant features. And so we wrote this batch job, we wrote this batch code. It works great. The boss is very happy, and he asks us, like, we need to put this into production, and we need to generate those features in real time. So now we're moving to the stream implementation. So let's talk a little bit about the difference between batch and stream jobs. So in a batch job, you optimize for throughput. So you care about how much data you can process. You read the data typically in bulk from, for example, a CSV file. And because of this, you can leverage data analytics library like pandas. On the other hand, in a stream job, you optimize for latency. So you receive a request and you want to reply as fast as possible. You receive data one record at a time. So you could receive your data from Kafka or a REST API. And the data is represented like one record at a time as a JSON dictionary or like a plain Python object, which means you cannot really use pandas with this data. So in this example, we'll use Kafka. If you're not familiar with Kafka, I'll give you like a 30-second introduction. It's a distributed streaming platform. It allows you to broadcast messages between services. And one key feature of Kafka that is very useful for us is that the consumer of messages, when they restart, they can replay historical data. So in our example, we require a history of the observations in order to calculate our features, which means that when our features calculation job dies in the middle of the day and we restart it, we can replay from Kafka the history of the observations. So then we've got all the data we need to serve accurate features without having to load them from a file or from a database. So our stream job looks like that. So it looks very similar to our batch job, except the data instead of coming from CSV file, from Kafka. And if we go ahead and do like a plain Python implementation of the job, we start receiving observations. So they look like this. They're like just one record put in a dictionary. And we would like to store those observations in a data structure that we can query efficiently. And the type of query we want to do is first, we want to find the bond based on their bond ID. So is it bond 007? Is it bond 008? So we'll first key the data by bond ID and store it in a hash map, which means we'll have very fast lookup of O of 1. And then the next thing we want to do is look them up based on the timestamp. So for this, we'll use a sorted list, and it means we can look them up in O of log n. So we receive observation, we put them in this complicated data structure, and then when we receive a prediction request, it means we can very quickly look up the information we need to put together the features. But what happened here is that in order to create this plain stream implementation, we had to come up with this complicated data structure, we had to write a lot of code that is very imperative, and it's probably has got a lot of bugs. And now we've got two different versions of the code to maintain, the stream version and the batch version. And like every time we have to change something, we have to change it in both places and make sure that they do the same thing, which is kind of a pain to maintain. And lastly, like plain Python can be quite slow and it can use a lot of memory. So it doesn't sound great. And we come to ask ourselves, would it be easier if we could just reuse the code we had written before to calculate our features? So the first step to do so is to prepare the streaming data so we can reuse our batch code. So if you remember, the batch code was just this function that was taking pandas data frame as input and spitting out pandas data frame as an output. But at the moment, we're in this situation where we're receiving JSON records one by one and want to convert them to a pandas data frame. It wouldn't be a good idea to take one JSON record and convert it to a data frame because it's not very efficient. Like data frame works much better if you have a certain amount of records in them. So instead of receiving data one by one, we're gonna receive the data in, we're gonna process the data in micro batches. So There's different strategies in terms of how you define your micro batches in your real-time job. You can batch your record by time, so every 100 milliseconds. You can batch your record by a record of the same size, so for example, 1,000 records. You can batch by a mix of both, but what we found worked best for us in terms of reactivity is to flush all the available messages that are in your Kafka buffer, because in Kafka, when you receive the message, they are being queued in a buffer, and you can read all of them. So then you'll use all the available information when you process the messages. So that's the first step. We've got our record in micro batches. Our first batch of message comes in. It looks like this. We've got, from the observations topic, we've got 3 observations. From the prediction request, we've got 1 request. We can easily convert it to data frames using the pandas library. We can do the same thing for the prediction request. And lastly, we can call our batch function to calculate the features. So you may think, oh, it's great, job done, but there's a few issues with this approach when it comes to using pandas. So imagine there's a second batch of record that comes in. We've got 2 observations and no prediction request this time. Then we convert the incoming observation to a data frame, and we need to concatenate those incoming observations to the existing observations. So we append to the table. And if you're familiar with pandas, you learn that concat is a very slow operation because it needs to copy the data. It's going to be a problem for us because we're going to have a long history of observations, and at every cycle, we're going to append like a few rows, but it's going to require us to do a very big copy. The other issue with pandas is that it's not exactly type safe. So because we didn't receive any prediction request, I can convert the prediction request to a data frame, but then I end up with this empty data frame that's got no columns, and it's quite bad. And you end up with code like this, where every time you've got a data frame, you have to check if it's empty. And if it's empty, you return an empty data frame. If it's not empty, you can do some processing. And this trickle downstream in all the code base, and it starts spinning bad very quickly. So we don't really want code like this. So to summarize what we talked about here about pandas, there's issue with concatenating. It's slow and it's not type safe. So can we find something better? So we're in this situation. We've got CSV, we've got JSON, we've got pandas. We want to go in between efficiently. And we're going to introduce Apache Arrow as an intermediate in-memory representation for the data to solve all those problems. So Apache Arrow is an in-memory format for tabular data. So think about it as a bit like pandas, but a bit more low-level and more focused in how the data is represented rather than being focused on how can I do like data wrangling. So let's give it a try. We'll install it and import it, and we'll see what it's like to convert the data using Arrow. So we go back to the beginning. I've got my first batch of messages coming in. And to convert the data using Arrow, one requirement is that I introduce a schema. So for every table, I will have to specify the schema of the table, which is just the name of the columns and the types. So it might feel like it's a lot of effort, especially if you're used to the ease of Python and not having to define any type, but it's very valuable, both in terms of type safety and documentation. And then I can convert my records to a table using the schema. I do the same thing with the prediction request. I introduce a schema, I convert the records, I've got my table, and then I can call calculate features by converting the Arrow tables to pandas data frame. And one advantage of Arrow is that those tables, to convert them to data frame is very fast because it's a zero copy operation. We're just creating a view of the table. And then the second batch of messages come in. I process the observations, I convert them to a table, and I can then concatenate the observation table with the new record. And in in Arrow, this is a very fast operation because it doesn't require any copy. We can do the same thing. So with the prediction request, we convert them, and you notice that this time we've got this empty table, but we still have retained the schema of the table. We still know that there's a timestamp and a bound, which means I can call the my function without it crashing, and we got rid of all the old smelly code that we had before with pandas, which is great. So to summarize with Arrow, we've got a type-safe environment. We've got fast zero copy concatenation of tables, and also converting to pandas is very fast and a zero copy operation. So what we achieved here is a unified data representation. We're able to represent the data in our batch jobs in the same way that we're represented in our stream job, meaning we can use the same code. The next step is to orchestrate the data flow in a similar way between the stream and the batch job. Let me talk about the specific challenges of orchestrating the data flow in a streaming job. So first, we want to manage the size of the batches that we receive from Kafka. So I'll talk about the different strategies for micro-batching. It's actually not that simple to implement, especially if you want to limit the size of your batches and not have too much data into memory. And the other thing that we need to manage is that we need to replay the messages across different data sources in the correct order. And what I mean by that is that in a specific example, to calculate our features, we need the history of the observations. And we cannot make prediction until we have received all the relevant observations. And more specifically, like if you look at this batch of messages, for example, you can see that the observations are from the beginning of the month of January, when the prediction request is from the end of the month. And this is typically what happens with Kafka when you start replaying messages, because Kafka is not going to replay the message in order when they come from different data sources, so from different topics. So these are key features that we would want for a framework when it comes to run or stream jobs. So we've looked at existing framework for streaming, and we actually didn't find one that was suitable for our problem space. And so there's a limitation we found with the existing framework. The key aspect of it is that most of those frameworks are optimized for latency, and they tend to process one record at a time. So what they're trying to do is deal with transactional workload, but we're more focused on analytical workload. Some of them are quite heavyweight libraries, so they require you to operate a cluster. Some of them are running in Java. Some of them have got intrusive APIs, so you'll have to rewrite your code in order to use the framework. Some of them only support linear workflow, so you cannot do joins between data sources, which is kind of a problem when you calculate features, because calculating features is 99% joins. And lastly, most of them don't solve the problem that I just explained about replaying data from different data sources in a timely fashion. So that's why at Treadwell, we came up with beavers to solve all those problems. And in a nutshell, beavers is a streaming processing Python library optimized for analytics. And it solved all the problems that I just mentioned with the other frameworks. So let's talk a little bit about how beavers work. So the first thing you need to do with beavers is you create a DAG. So a DAG is a directed acyclic graph, and it's basically a way to orchestrate your computation in a streaming fashion. So in your DAG, you've got three types of nodes. At the top, you've got the sources. So this is the input coming from the outside world. So where does the data come from? In between, you've got the computational nodes, and those computational nodes are just Python functions that have been wrapped and put in the DAG. And lastly, you've got the sinks. So this is the outputs of the DAG. And the edges, so the connection between the nodes, they represent the input of the Python function, so their parameters or their arguments. So we'll start by looking at the API we have to build a DAG. So we create a DAG, and first thing is we create the source node. So for source node, we just define a name and a schema. The schema is optional, but it allows you to solve the problem we've seen before, where you've got a lot of empty data frames with no schema that creates a lot of issues in your code. So here I define my observation and my prediction request source. I can then add computational nodes. One important note about computational nodes is that we have two types of nodes. We've got stream nodes. They compute ephemeral events, and those events only live for one cycle. During the next cycle of update, we forget about them. So the features, for example, we calculate them, and then at the next cycle, we don't really care about them. We can just replace them with an empty value. And then we've got the state node, and the state node are persistent from cycle to cycle. So for example, the observation history, we want to keep that from one cycle to the next, even though there were no new observations coming in during that cycle. So these are key features that we borrowed from Kafka SQL, if you're familiar with this framework. So here we're going to add the observation history node. So it's just a node that when it receives new observation, you will append them to a table and keep accumulating them and return this whole history. So we add it to the DAG by putting the function in the DAG and then connecting it to the observation source by calling the map function. And then we can add the features calculation to the DAG. So the feature stream will be connected to the observation history and the prediction request source. And an important thing for stream node is that we have to specify the empty value. So if they don't update, we can replace the empty value with something meaningful. So we again avoid this issue with the smelly code we talked about before. And lastly, we've got sync node. So for sync node, we just give them a name, and that's the output. And so we have a DAG here. And so far, we've only focused on putting the business logic in the DAG. We haven't said where does the data come from. And so that's what we're going to talk about now. So there's essentially three ways to provide the data and execute the DAG. One way is to do it manually. So you will set the inputs of each node yourself, execute the DAG, and look at the output. That's good for unit tests, but it's very labor intensive. The second way is to do it in live mode with Kafka. And the third way is to do it in replay mode with files. So we're only going to really talk about the live mode here because we don't have that much time. We have our DAG. We want to specify where does the data come from. So for each source in the DAG, we'll specify the name of the topic in Kafka, how the data is deserialized. So in our example, we've been using JSON, but you may want to use protobuf or Abro. It's up to you, really. We don't have any opinion on how the data should be represented. And lastly, the offset policy. So the offset policy basically says, like, how far in the past you want to replay the data. So in our example, we want to replay the whole history of the observations that's available in Kafka. But for prediction requests, we only care about the latest one. Then we do the same thing for things. We specify the name of the topic and how it's being serialized. And that's it. We can just run it, and we've got our live job running and calculating features in real time. So it looks a little bit like this. So all we did is we took our DAG and we just connected the inputs and the output to some Kafka topic. And I'll briefly talk about the replay mode. The replay mode is it allows you to run your DAG with data that's stored in files or in the database. And it's good if you want to test your DAG with historical production data, or if you want to backfill some data, so you change some parameters and you want to backfill the history. And it's also very useful for profiling if you find that your DAG in real time is a bit slow and you want to figure out where does the slowness come from. And essentially what you would do is you just specify, where does the data come from and where does the data go. So instead of specifying Kafka topic, you just specify files, CSV, Parquet, or whatever you want to use. And with this, we've achieved like a unified data orchestration, which means we can use our stream job and our batch job in a similar way. We've got one DAG, and we can run it in both modes. So in conclusion, like what I would say is like you can unify batch and streaming with Apache Arrow and beavers. You'll only have, if you do so, you'll only have to implement your job once, and you'll save memory and you'll increase throughput by using this approach. So thanks for your time. If you get a chance, please give it a star on GitHub, and you can play around with it by just installing it with pip. All right, thank you very much.
Hi, Arthur. Thank you so much for that talk. That was great. We have a few minutes left that we can take some questions. I guess we do have one going up. There are a couple coming in. First, yeah, you see that? Okay, show it. There you go.
Yeah, sure. So yeah, that's a good question. So I could provide the resources, yes. Let me find them because it's briefly mentioned in our documentation. So I will post a link up. So I'll post a link in the Q&A, in the chat, sorry, to answer this question. If you go in this section of the doc, the top is the top explains like how you can manually unit test your DAG, and it shows that it's quite labor intensive and there's better ways to do it, but it's still a useful feature. Okay, we've got another question.
Yeah.
So yes, beavers is implemented in Python indeed. And I know that there are some other similar frameworks implemented in Rust, for example. But what we find is like actually, like you may say, oh, Python is a bit slow. Why would you use Python to do that? But beavers doesn't do a lot of work actually. Beavers just orchestrate the data flow. The heavy duty is done by the function that are being called by beavers, and typically those functions should call like code like Apache Arrow or pandas, which will then call like native code written in C++ or C or Rust. So you're essentially just orchestrating some heavy-duty tasks that are written in Python. Yeah.
I think you have one more there, Arthur.
Can you? I guess not really. So I mean, you can do anything you want. Essentially, the node in the Python DAG are Python functions. So then you could call some stuff done in dbt, or maybe DuckDB, for example, if you're using SQL. But it's not SQL focused. We mainly focus in orchestrating tasks that have been written in pandas, polars, or Arrow.